In this video, we'll introduce the Secant Method root finding algorithm. After studying this video, you should be able to explain how the Secant Method root finding algorithm works and use MATLAB to implement the Secant Method. Here's the basic idea. Recall Newton-Raphson. Here's our iteration scheme where xi plus 1 is equal to xi minus f of xi divided by the derivative, f prime of xi. And again, f of xi, important to note, that's our roots problem formulation. Such that f of x equals 0. And remember, we're trying to find that value of x. That's our goal. Again, just reviewing a little bit about what is a roots problem. So, one of the issues with Newton-Raphson that I identified at the end of that video was this calculation of the analytical derivative and the fact that sometimes that can be a bit cumbersome. And the basic idea of the secant method is to replace the derivative in the Newton-Raphson algorithm with a finite difference approximation. So if you recall the definition of a derivative, df dx is equal to the limit as delta x goes to 0 of f at x plus delta x divided by, minus f of x all over delta x. Well, for a finite difference, what we do is we just eliminate that limit, and it'll be an approximation for small delta x. And so we will use that here, where here is, we can imagine x sub I is equal to xi minus 1 plus some delta x. And then we have a finite difference approximation. Now, it doesn't really matter how accurate this approximation is in this case, because remember, all we're doing is using this to get an educated next guess for our root finding iteration. We're not trying to approximate the derivative. We're just using information about how is the function changing, what is the slope of the function, in order to calculate our next guess. So if we take this result and plug that in up here for f prime of x and simplify, we get the following iteration scheme that we can then implement in MATLAB. So let's look a little bit conceptually about how this is going to be different. So let's say here is our x1. Well, the first thing we need on the right hand side, it requires two previous values. That means we need two initial guesses. Not really a big problem. What we can do is just take another second initial guess, let's call it x2, that's close to the first one. Remember, the closer they are together, the closer a finite difference approximation comes to the actual derivative definition. And so we'll use those two to calculate the slope, and just like before, we'll use that calculation now to come down and get some x3 and go up to a function evaluation at x3. Now, for our function evaluation at x3, what we're going to do is still use these 2 points. So now it's not really a tangent line anymore. It's a secant line connecting through 2 points on the curve, hence the name secant method. And then we'll continue that line all the way down to the x-axis and then go up. So that would be our x4. And then for our third iteration, we do the same thing. We connect this point and continue that down, and eventually we hit that root. So the secant method looks like it will exhibit similar convergence behavior to Newton's method, which is good, and because that's fast. And it doesn't require calculation of that analytical derivative. So let's look at MATLAB implementation. Actually, I'm going to let you write this one. So here's some hints. We're going to do this as part of the programming assignment. And some hints on how to approach this. First, since this is so similar to Newton-Raphson, use the Newton-Raphson M file as a starting point and just modify that M file so that it implements the secant method. And the two main modifications you're going to need to do is, instead of inputting the function and the analytical derivative of the function, you're going to need to input the function and two initial guesses. Also, during the iteration, you're going to need to always store two previous guesses for each iteration. Remember, I'm using the term guesses. These are the root estimates for each iteration. So I think you'll be able to do that as part of the programming assignment. And let's finish up this video by talking about some pros and cons of the secant method. A big pro, it has the same quadratic convergence behavior as Newton-Raphson. So we know that it is efficient. We like that. Another pro, in contrast to Newton-Raphson, is it avoids calculation of an analytical expression of the first derivative, which is sometimes cumbersome. Now, this wasn't a big deal in the example with the exponential function that we've been using, but it could be a big deal in lots of other situations. One con, similar to Newton-Raphson, some functions are going to show slow or poor convergence. And this is the same figure I went through for Newton-Raphson, basically showing different situations where the algorithm does not converge on a root because of how the function is behaving. Things that cause problems are inflection points, local maxima and minima. Here's local maxima and minima, these last three examples. Those are things in functions that can cause problems. Just to elaborate a little more on what I talked about in the Newton-Raphson video. Secant method and Newton-Raphson have a lot in common. They're both examples of what we call open methods for root finding. And that's as opposed to a bracketing method. And that bracketing method is bisection. And that concludes this video.